me just go back to this picture of this MOS cap that I had. Okay, MOS capacitor, 2-terminal device that I had, metal, oxide, okay, and then I apply a VG and I apply a body, right, let me call this gate. Now as I sweep my VGS from a negative value to positive value, right, what do you think will happen to this capacitance of this device? Okay, I am going to now do a CV plot. C versus VGS. If VGS is negative, then what happens? By the way, let me also put the thing. This is P-type substrate. VGS is negative. What region of operation is this in? Accumulation, right? So that means you will have a lot of holes sitting here. Right? Now if the concentration of holes is so high at the surface, any negative charge that you put here is effectively going to be terminated right at the surface. The electric field will terminate right at the surface because the concentration of holes at the surface is that much higher. So of course there will be depletion region and all that, which is negligible. All I am saying is it is negligible. So if you look at this capacitance, this is going to be just that parallel plate capacitance, which is epsilon naught WL by Tox. Okay, so of course this is my L. W is into the plane. Right, and this is my Tox. So C naught prime was Cox, or let me just call it C naught, Cox into W into L, correct? So this capacitance will just look like this. Now what do? I move this into the positive region, VGS. VGS is going to be greater than 0, and then which region will it start operating in? Depletion mode, right? So if you look at this, I am now going to put positive charges here because VGS is greater than 0. This will start depleting my channel. These are immobile carriers again. In the depletion mode, obviously there is negligible surface charge, right? So the electric field will actually start from the positive charge and terminate deep into the channel also, like this, you know. So therefore, if you look at the capacitance in this depletion mode, it is going to be a capacitance of the oxide plus, not plus, in series with a depletion capacitance. Obviously, if you put two capacitances in series, then it sort of drops. It's C1 C2 by C1 plus C2, and therefore this capacitance will now drop. Okay. Now at some point the surface charge density starts increasing again, and when you reach inversion mode, the surface charge density will be so high, right, that I have been able to terminate all the electric field almost at the surface. So therefore the capacitance will now simply go up back to this old value that we had. This is just a sweep of capacitance versus VGS. Once it goes to the so So what do you think it will be? Okay. So, okay, so maybe I'll discuss this offline with you, but typically the picture is a little naive here that I've shown you. When you do it, things will change in a sort of a gradual manner, right? In fact, if you look at this picture, capacitance may start dropping like this itself. It's not so abrupt as I have shown here, okay, but there will never be a discontinuity because nothing is abrupt in reality, okay. But anyway, so I just want to point out that there is this picture. Now, where are we going to operate this device, our transistor in, and what capacitance should we worry about? Should we worry about this value? Should we worry about this value? Or should we worry about this value? So let us say that the device is in linear region of operation, transistor. Where is it on this picture? Right side, it has already got inverted. So really, if you look at the region of operation, we are worrying only about to the right of this region. Even in linear operation, what I don't want you to assume is linear region means it's in depletion mode. No. When it enters linear region, it has already, channel has got inverted. That's how we have exceeded threshold voltage, right? Of course, it may not be as strongly inverted as it would be in saturation. That is fine, but still the capacitance is effectively this capacitance that we are talking about. And of course, as you just saw in the earlier picture, when we discharge the capacitor from VDD to VDD by 2, we are only in saturation region. Forget about linear region at all. We are not even entering that region. So clearly, we are only worried about this capacitance here, which is equal to C aux into W into L. Okay. So with that, I can move into the picture of the capacitance for an NMOS transistor or a PMOS transistor actually. It's a 4-terminal device. It turns out there are capacitances all over, okay, from all these terminals. This is gate, drain, source, body. Without loss of generality, I am just saying one is drain, other is source. Okay, here I have a capacitance like this, CGD. I'll tell you the origin of all of these capacitance, CGS. Then there is CGB. Then there is, CDB and CSB. Okay. So now we first consider the regular device where the manufacturing was perfect, in the sense that if I have my oxide thickness here, then wherever this diffusion finishes, exactly there the gate will start. Okay, this in fact is manufactured in something known as a self-aligned process. You grow the silicon, make everything silicon dioxide, then put a mask and then harden one region and make the other soft. Then you etch out the soft regions. So because the gate oxide is itself acting as its mask, right? It is a self-aligned process, and typically I will get a nice diffusion region exactly like this. Wherever this diffusion finishes, exactly there the gate will start. Okay. So therefore the total gate capacitance CG is basically just CGS plus CGD plus CGB. Okay, I am writing this as 3 components because when you now go into saturation region, right, suppose this is my source and this is the drain, VD, VG and this is VS, okay, and body is also grounded. When you go into saturation region, I told you that the channel will pinch off, which means there is more charge on the source side than the drain side. So there will be a uneven distribution of capacitance actually in this kind of region. So what I am saying is the total capacitance CG, which is a sum of CGS plus CGB plus CGD, right, is just C aux into W into L, sum of these. But if you look at the distribution across various regions, in cutoff for example, CGB will be whole of C naught and CGS and CGD will be 0. Okay, this is just a sort of a distribution model that people have done. It's more relevant for analog guys, not for digital. Okay, if you look at the saturation region, the CGS will be more, CGD will be less and the CGB is just made 0. So all I am saying is this total capacitance which I have called C naught is being distributed across these 3 components. For digital purposes it does not matter because we are looking at the sum of these 3 components always. For analog guys you have to worry about these AC values also, and therefore you look at whether the source has more capacitance or drain has more capacitance and all that. Okay, this is the ideal picture. Now what do you do after manufacturing it? You form your diffusions, implant N plus, then you have to anneal this device. When you anneal this device, these regions, right, will expand thermally like this. This is not depletion region I am talking about. The atoms will actually move because I am heating them. I am taking this to like 800 degrees centigrade. You have to anneal it in order to make all this even out, to even out all the manufacturing defects. In that process, the N plus will now diffuse under the channel as well. So what will happen is there will be a small overlap capacitance that comes here. This distance is called L overlap. Okay, so previously if you look at it, my channel length was this. Now after this diffusion, because of annealing, my channel length has become only this much. Okay, so what is my overlap capacitance? C overlap is, it's just like a parallel plate capacitor again, it's this part of the gate. How much capacitance is that going to form? The area is L overlap into W, right? So this overlap will be C aux into W into L overlap, right? So the net gate capacitance is CG plus twice C overlap, one for the drain side, one for the source side. So this I can write as C aux into WL plus C aux into W into L overlap. Okay, again note, what we have done is we have written all of this as some technological constant parameters into the design parameter. What is our design parameter? W and L. For digital design, even L is not a parameter, right? Even that is fixed at the shortest length. So this is basically W into C aux into L plus C aux into L overlap. What is the conclusion? If you increase the width of the transistor, the gate capacitance goes up. Okay? Any questions here? Yeah. Yeah. So finally, when I tell you what is L, right, that is accounting for all this. When I say W by L, whatever L you substitute there actually accounts for all this. Okay, they may start, for example, at 20 nanometer and eventually it will come down to 14 nanometer or something like that. And in the actual model, if you look at the model file that has been given, they do further calculations to reduce this L. You say L is so much, but internally that L will be reduced, and then that L will be plugged into the model for the current equation. Okay, remember now there is also a depletion region of this N and P junction, so there it will further reduce. So all of that will happen. Okay, yeah. Oh, because I have one capacitor overlap on the drain side, one overlap on the source side. Where? Huh? Oh, sorry. This one. Yeah, this is 2. Yeah. 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 No, be careful. C naught or C ox. C ox is just epsilon by T ox. Epsilon naught by T ox. No, that's why I'm saying that I have called C naught. I'm calling that C naught. Correct. Yeah, correct. No, that's what I'm saying. Be very careful here. This is not because, these two are not because of overlap. I am saying this is actually a combination of whether the transistor is in saturation mode or linear mode or cutoff mode. If the transistor is in cutoff mode, then this CGB is C naught. CGS and CGD are 0. If it is in linear mode, then it's like the charge distribution in the channel is uniform, right? So therefore, CGS and CGD are just C naught by 2 each. And the third condition, when it is in saturation, there is an uneven distribution where there is more charge on the source side rather than drain side. Therefore, that capacitance again changes. So that's why I said the first picture is even without considering overlap capacitance, I have to write the capacitance as a component of 3 things, right? Yeah, but for digital circuit purposes, just assume that is C ox into WL, sum of all these. That is not overlap capacitance. Okay? Yeah. So it's between gate body, gate drain, gate source. So the actual picture, if you want, is if you are doing high frequency analysis, then the way the charge changes under the drain and the way the charge changes under the source will be different depending on where you are operating the transistor. Therefore, the capacitances will change. So it's not just all 3 of them. It's not just CGB. CGB is when you are in cutoff region, right? And it's mainly in accumulation mode or something. Then it is just between the body and this. That's all. Yeah. In the total gate capacity, the L which we take is the reduced L or the original. This L here, right? This L here. That is the reduced L. Yeah, that has to be the reduced L. Okay. So now the other two components, which are basically CDB and CSB. The origin of these capacitances are your PN junction diffusion the PN junction reverse bias capacitances. Okay, so if I have a PN junction like this, right? This is my P, this is N. I have a depletion region here, right? Then this, there's a total distance of WD. This will now form a capacitance, right? And give rise to a capacitance in that PN junction. Okay. If I reverse bias this further, what will happen to the depletion region? It will increase, right? If I increase my reverse bias, the depletion region will go up like this. So what will happen to the capacitance? Yeah, so what will happen to the capacitance? It will come down, right? So the key thing is that it is a function of the applied voltage also. Okay, so if this is my applied voltage V, then if V sort of is less than 0, it implies capacitance also decreases because depletion region goes farther and therefore it comes down. Okay.